Hi everyone, welcome back. Today's video we're going to be looking at the average value of a function. And before we start with the process for how to find this average value of a function, what I want to do is I want to start by looking at this number set that I have here on screen, which consists of 3, 5, -1, 2, -1, and 4. And what we want to do is, again, find the average of that data set. So let's go ahead and let's go and find the average for that data set. So to find the average, what we typically do is we add all the numbers together that are given to us. So 3 plus 5 plus -1 plus 2 plus -1 plus 4. And then we divide that average by the amount of numbers within our data set. So in this particular instance, we have a data set that contains 6 different numbers, so we divide by 6. Now, when you take 3 plus 5 plus -1 plus 2 plus -1 plus 4, then we get 12. And so here we then get 12 divided by 6, which then gets us an average of 2. And so the work that we're going to be doing in this particular section takes the same amount of, or takes the same process. It takes the same process, but this time we're going to start doing this for a certain interval or for a certain function that's given to us. Now, in order for us to be able to extract that, we're going to need the graph. So let's go through and let's focus on that graph. All right, so what I want to do here is, again, I just want to create this function so that I can see what's going on with this function, and I can try to interpret how we're going to extract some average value. Here we go. Perfect. Okay, so I have my y, and I'm going to have my x values here. And so my function f of x, let's call this function f of x, is going to be bounded by some interval between a and b. So we'll go between some a value and some b value. Well, in order to start looking at the average values, what we're going to do is we're going to then start translating all of these averages, or all of these numerical values. The numerical values that were given in the data set, we can view those values as the output of a function. In other words, the number that corresponds to the y value that your function outputs. So if x was some random number, then the function evaluated at that number would be 3, and that's what the first number tells us. A function evaluated at a different number would get us 5, so on and so forth, to produce all these numbers. So the big question then becomes, how do we get an average from that? Well, if we start looking to find an average, I'm going to abbreviate average as AVE. So this notation, F, and I have a subscript here denoted as AVE. This corresponds to the function average. So my function average for f of x, this is going to depend. What we're going to have to do here is we're going to have to take the addition of all of these, let's call them sample points, and more specifically, their sample outputs. All right, so once you choose a sample point, or a sample point for the x value, we plug it into the function f of x, and we get an output. That output we could then start adding together as such. Now, we're going to do this an n amount of times. And so what does that mean for us? Well, what that's going to mean for us here is that if we have an n amount, in other words, 1, 2, 3, 4, 5, 6, that was the n amount of 6. In here, we just have an n amount all the way up to some random number, which means we're going to divide by that nth amount. Now, what does this mean for us? Well, let's look at my interval from a to b. If I were to take my interval from a to b, and if I were to subdivide that interval, meaning that I take my delta x and I subdivide this into n subintervals, then what I'm going to be looking at in this particular instance is going to be this subdivision of the interval that has very small intervals. And within those intervals, we're going to be able to find any random sample point. So we can choose any value, let's call this x sub I here, inside of this interval where we're going to have x sub I minus 1 and x sub I. So we have, again, some random sample point inside of this interval. And that sample point will then get us an output. That output value is the function evaluated at the sample point. And again, what we're doing on this right-hand side is we're taking all of these outputs, all of these functions evaluated at the sample points, and we're adding them all up. In other words, we're going to find the average of the y values. So that looks like it's easier said than done, but it's kind of nice. Now, looking at the formula that we've written so far on the right-hand side of the screen, we are dividing by n. But if we can go through and if we can interpret my n value according to the delta x subdivision, then what can happen here, if we solve for n, then what we get when we solve for n, whoops, let's make that better, there we go. When we solve for n, then we get that n is equal to b minus a over delta x. And that's going to be important for us to have because now my function, or this formula that I've written, then carries over. We could then talk about this formula. Let's copy that downward. Okay, that looks not too well, but we'll make it work. Whoops. Again, technical difficulties, but we work through them. Let's see. There we are. Okay, so what I have here is, again, I have that formula written down. And then instead of n in my denominator, I'm going to substitute that n for what we just found, which is that n is equal to b minus a over delta x. Now, b minus a over delta x, that's in the denominator, which will make this a complex fraction. And if it's a complex fraction, we can alleviate that by multiplying both numerator and denominator by delta x. So this now will then become something real nice. And let me actually get rid of this here. There we go. So let's get rid of that. And this is now going to be my b minus a. Delta x is now going to be multiplied on this numerator. And let's go ahead and let's rearrange this. Let's put this in the spot where it's going to go. No. Let's try that again. Sorry, I was talking to the computer. There we are. All right, and again, the numerator, that's being multiplied by delta x. There we are. So we simplified the complex fraction, and now it looks like this. But I want you to start looking at the piece inside of the brackets, that formula inside of the brackets. That formula inside of the brackets, that can actually be condensed by a summation. Oops. So that can be condensed by a summation. If we begin I at 1 and stop at n, then that's going to be the summation of all of these sample points of x sub I. And of course multiplied by delta x. And then all of this is being divided by b minus a. So we'll keep that b minus a in our back pocket for now. There we go. Oops. For some reason my pen doesn't want to work that well. It's all right. There we go. Now the summation is only focusing on the function outputs, which means b minus a has no effect, or this summation has no effect on that b minus a. So naturally what we then have is that we have 1 over b minus a multiplied by the summation from I beginning at 1 stopping at n for all of these sample points of x sub I multiplied by delta x. But that in this summation looks oddly familiar. It looks oddly familiar because that now reminds us, or it should remind us, of a Riemann sum. A Riemann sum can then be expressed as an integral, as a definite integral. So if we follow this whole logic then we're left with the average of a function is going to be a firm equal sign if we then take all of those subintervals and subdivide them infinitely. I beginning at 1. Oops, excuse me here. Cheese and crackers. Sorry, that's 1 over b minus a multiplied by the limit as n tends to infinity for the summation of I beginning at 1 for f of x sub star I delta x. But again, this is the limit definition for that Riemann sum definite integral, which means I can represent that Riemann sum as a definite integral. And here we have that the average of a function can then be calculated by the integral of the function from a to b divided by the difference in that interval. Therefore, we don't have to go through the whole process of identifying each individual output, dividing by how many outputs or how many n values we then observed. We can go through directly and just use calculus to extract that this is going to be just an integral for the function from a to b, and it's going to give us some value. Now, what is that value that we get then? Well, the value that we get is the average of the outputs. Therefore, if we want to take all of these outputs, all of these continuous outputs here from A to B, average them together, we could extract some value, and again, this is just some random value, we'll call this C, such that the function evaluated at C will give us that function average. And that's what we want to see, that this function will in fact get us an average, and that average is going to be some y output on the function itself. So let's go ahead and let's state this using a theorem. So we're going to be talking about the mean value theorem for integrals. All right, so here's the example that we're looking at, and we have the mean value theorem here for integrals as well. So the mean value theorem for integrals says that if f is continuous on an interval from a to b, then there exists a number c in the interval from a to b such that the value for the function, when evaluated at f of c, this is equal to the average. So in other words, we want to find the c value inside of the interval from a to b such that the function evaluated at that number will equal to the function average. And the function average is this function average that we derived at the very top. In order to illustrate this, we're going to go on to this example that says find the number c such that the average function is equal to f of c for this given function, which is 8 minus cosine of x divided by 4 on the interval from 0 to 4 pi. So in order to do this, we're going to go through and we're going to find the average first. So finding the average of this function is going to involve finding the difference b minus a. So b minus a for us will be 4 minus 0, so 1 over b minus a, multiplied by the integral from a to b, from 0 to 4 pi, for the given function that we integrate. So in order to simplify this, or in order to integrate, I'm going to simplify really quick. 1 over 4 pi. The integral of 8 with respect to x is just 8x. The integral for the integral for negative cosine of x to the 4, x divided by 4, we can use a u substitution for the denominator. Sorry, I meant denominator, I meant inside argument of cosine. If u is equal to x over 4, then we naturally get that dx is equal to 1/4 du, du is equal to 1/4 dx, and therefore dx is equal to 4 du. And so when we do this, we get negative 4 sine of x over 4, evaluated from 0 to 4 pi. And when we evaluate 8 times 4 pi, that gets us 32 pi minus 4 times sine of pi fourths divided by 4, which is just pi. And notice that if I insert 0 into 8x, that gets me 0. 0 into x here for the argument of sine will get me sine at 0, which is just 0. So what I have left is this. Now sine at pi, that's going to be 0, so that goes away, and all that we're left with is 32 pi divided by 4 pi. 32 pi divided by 4 pi is just 8. So now that we have the average value of the function, we're going to go through and we're going to find what is the c value on this given interval that works. So here we go. I want my average. So my average, the one that I just found, I wrote 4, but I meant 8. There we are. F of c. This is going to be my function evaluated at c. This is going to be 8 minus cosine of c divided by 4. And again, because I'm evaluating at c. Subtract 8, we get 0 is equal to negative cosine of c over 4. Multiply by a negative, and we get that 0 is equal to cosine of c over 4. So the big question now is a trig question that we are trying to find for what c values will the ratio for cosine evaluate to be 0. So what c over 4 values get us a cosine of 0? Well, cosine on the unit circle is only 0 at pi over 2 and at 3 pi over 2. But those are just pi increments, so we're just going to increment by pi. And therefore, to find those c values, we multiply both sides by 4. And pi over 2 multiplied by 4 will get us then 2 pi. Pi k times 4 will get us 4 pi k. So let's pick k values. If k is equal to 0, then we naturally get that c is equal to 2 pi. If k is equal to 1, then we get 4 pi plus 2 pi, which is 6 pi. Notice that's outside of our interval bounds, so therefore k cannot be anything greater than 1, because anything greater than 1 would just keep adding 4 pi to that. Well, let's just double check, just for good measure, k is equal to negative 1. So if k is equal to negative 1, this is going to be 2 pi minus 4 pi, which will be negative 2 pi, which again, not in our interval. Therefore, the only value in our interval is when k is equal to 0, in other words, when c is equal to 2 pi. So the question at hand was find the number c such that the function evaluated at that point will give us the function average. And just to double check, this function evaluated at c, so the function evaluated at 2 pi, will then get us 8 minus cosine of pi halves, and cosine at pi halves is 0, which gets us our average value. And therefore, the value that we found is c is equal to 2 pi. And there it is. So there's a work that went into this, and we are going to have more examples to look at, and we're going to want to look at those in class. So I hope you all enjoyed this lesson, and stick around and we'll be covering some more calculus. Till then, please stay safe.